When NASA launched the James Webb Space Telescope, the world expected revolutionary discoveries, and now, yet another incredible milestone has arrived. In a distant, young star system still forming its planets, the James Webb Telescope has detected something stunning: the unmistakable signature of frozen water. Not just water vapor or traces of hydrogen and oxygen. This is solid, icy water found in a region where planets are just beginning to form. This detection, coming from over 450 light-years away in the Chameleon I cloud complex, marks a major first in the history of space science. It's proof that the essential ingredient for life, water, is present in the raw building blocks of new worlds. To understand why this is such a big deal, we have to consider how planetary systems form. In the early stages, dust and gas swirl around a newborn star in a structure called a protoplanetary disk. Over time, these particles stick together, forming pebbles, rocks, and eventually full-sized planets. But for life as we know it to have any chance of existing, water must be available at some point in the process. Until now, astronomers could only speculate whether ice, specifically frozen water, was present in these disks early enough to be incorporated into the emerging planets. Now, thanks to Webb's unmatched sensitivity, we finally have hard evidence that ice does, in fact, exist in the early phase of planet formation. The telescope focused its powerful instruments on a specific young system known as IRAS 15398-3359, a relatively small protostar located in a dense cloud of gas and dust. Even though this object is only about 100,000 years old, a cosmic newborn, it already has a developing disk and an outflow of material that indicates active formation. When Webb observed this system, its near-infrared spectrometer picked up unique absorption lines in the light spectrum, lines that precisely match the molecular signature of water ice. This means frozen water is present on the grains of dust floating in the disk. These are the very materials that will go on to create planets, moons, and perhaps even comets in this young system. What makes this observation even more exciting is that it supports one of the most important theories in planetary science: that Earth-like worlds may acquire their water not just from internal geological processes or late-arriving comets, but right from the very first ingredients in the disk. If frozen water is present so early, then the chances of forming watery worlds around other stars, possibly even habitable planets, are dramatically higher than previously assumed. And since this system is very similar to what our own solar system might have looked like billions of years ago, it offers a direct window into how Earth may have gotten its water. But Webb didn't just detect frozen water. It also picked up several other types of ices, including frozen carbon dioxide, methane, and even more complex organic molecules. These frozen chemicals are the raw ingredients of life, the basic components that, under the right conditions, can form amino acids, proteins, and eventually living cells. That means this single young star system contains nearly everything needed to start a biological chain reaction, provided the right environment forms around it. In a way, Webb didn't just observe ice, it may have captured a snapshot of life's potential in its earliest, most fragile form. Of course, finding these ices wasn't easy. The Chameleon I cloud complex is incredibly dense and cold, which makes it ideal for preserving frozen materials but also extremely challenging to observe. Earlier telescopes like Spitzer and Hubble could barely penetrate the thick dust, but Webb's powerful infrared sensors were designed exactly for this type of work. It can peer deep into these dark regions and detect faint heat signatures or light absorption that reveal the chemical makeup of even tiny ice particles. The level of precision Webb brings to this field is truly unmatched, and this discovery is likely just the beginning of what it will uncover in the coming years. Scientists working with the Webb data have emphasized how critical this finding is for building a clearer picture of planetary formation. Previously, our understanding was largely based on computer simulations and sparse observational data. But now, with direct measurements of ice and other materials in young star systems, astronomers can finally compare their models to reality. Every piece of new information helps refine our theories about how common water might be across the galaxy and whether other Earth-like planets are likely to form with the conditions necessary for life. It also opens the door for deeper philosophical questions about life in the universe. If water ice is common in protoplanetary disks, then it's possible that the process of life formation isn't rare or accidental. It might be a natural outcome of planetary formation itself. That's a huge shift in thinking. Instead of wondering whether Earth is an anomaly, we might start asking how many Earths are out there. And each new discovery, like this one from Webb, pushes us closer to answering one of humanity's oldest and most profound questions. Are we alone? It's worth noting that this detection didn't happen by accident. It was part of a focused scientific campaign called the Ice Age Project, a multi-institution effort aimed at mapping the presence and variety of ices in multiple star-forming regions. Webb's advanced instruments allow researchers to study these materials with greater clarity than ever before. And IRAS 1539833359 is just one of many systems they plan to examine. This is only the first in a long series of investigations that will provide a much broader picture of how chemical ingredients evolve from clouds of gas into planetary systems. Detail is the size and composition of the dust grains where the ice was found. Webb's instruments revealed that the frozen water and other chemicals are forming on tiny grains of silicate dust, similar in makeup to what we find in meteorites and comets in our own solar system. These grains are small but incredibly important. As they clump together, they form the seeds of planets, carrying with them their icy cargo. That means the water we drink today may have once existed as microscopic ice crystals on dust particles just like the ones Webb observed billions of years ago. The fact that these grains are icy also has implications for the types of planets that might form in this system. Icy grains are more likely to stick together and form massive, gas-rich planets or ocean worlds. So, in addition to offering clues about water delivery, this finding may also help predict the types of planets that will eventually emerge around IRAS 1539833359. It's a stunning glimpse into the future of an alien solar system, a place where even now new worlds are beginning to take shape from clouds of ice and dust. This discovery also builds on recent observations that Webb made in other regions, such as the Orion Nebula and Taurus star-forming complex. In those cases, scientists saw complex organics and gases, but not much frozen water. That makes this new finding even more significant, because it's one of the first times that solid ice has been conclusively identified in such a young and actively forming region. It suggests that the presence of frozen water isn't limited to older or more stable systems. It's there right from the beginning, quietly building the foundations of planetary systems that may one day be home to life. As we look deeper into the implications of Webb's discovery, it becomes clear how significant this moment truly is for the future of space science. Until now, most theories about early water in solar systems were built on indirect observations or educated guesses. But Webb has given us direct proof, actual icy particles forming inside the nursery of new worlds. This is a dramatic leap forward because it turns the theoretical into the observable. It moves science from "we think this happens" to "we have seen this happen." That one shift makes all the difference in how confidently we can understand and model the process of planet creation across the universe. Another important factor is how early this water ice appears. The system Webb studied is incredibly young by astronomical standards, just 100,000 years old, which is barely a blink in cosmic time. And yet, even at this early stage, frozen water is already attached to dust grains, floating in the disk and ready to become part of whatever bodies eventually form. This means that water delivery might not be something that happens late in a planet's history, like when comets bombard it millions of years later. Instead, water might be an ingredient baked into the planet from its very beginning. This raises exciting questions about how many planets out there could be forming with water from the start. If every young disk like this one has frozen water embedded in it, then potentially billions of planets across the galaxy are born with a head start toward habitability. That doesn't guarantee they'll become Earth-like or host life, of course, but it does increase the odds. We used to think Earth might be special because it had water. Now, we might discover that planets with water are actually very common, and maybe Earth is just one example in a long list of watery worlds. Webb's discovery also brings new attention to the role of comets and icy asteroids in water transport. In our own solar system, many scientists believe that much of Earth's water came from cometary impacts during its early history. But if planets already contain ice during their formation, then the role of these late-delivering bodies might be smaller than we thought. Or perhaps both mechanisms, early ice and later cometary bombardment, work together. This layered understanding opens up new areas of research, especially as scientists try to match what we now see in distant systems with what we know about our own. Another fascinating layer to this discovery is the complexity of the ices Webb identified. We're not just talking about frozen water. There's frozen carbon dioxide, methane, ammonia, and even complex organic molecules. These chemicals are often referred to as prebiotic, meaning they're the kind of building blocks that can, under the right conditions, lead to the emergence of life. That doesn't mean aliens are forming in this disk right now, but it does suggest that the ingredients are there. And in science, the presence of ingredients is the first step toward understanding the recipe for life. This leads to one of the most exciting questions. Could life begin earlier than we ever imagined? If icy grains already contain life-forming materials before planets even finish forming, then it's possible that primitive biology could begin almost as soon as a planet becomes stable. This would completely shift the timeline scientists currently use when searching for signs of life on exoplanets. Instead of assuming life takes billions of years to arise, we might find evidence that under the right conditions, it can begin much sooner, perhaps even while a planet is still in its chaotic volcanic youth. The technical side of this discovery is just as impressive. Detecting ice from such a far distance, over 450 light-years, is no easy task. Webb had to pick out extremely subtle absorption features in the infrared light passing through the disk. These features are like fingerprints, tiny dips in light that match specific molecules. It's a bit like trying to hear a single whisper in a roaring crowd, but Webb is sensitive enough to pick it out with astonishing clarity.